Hello everyone, so welcome back to another one of my videos. As you can see, this video is a bit different. I am at the Astro campus and today I'll show you how I got to take these pictures right here, and I'll show you how I took them, and hopefully this video will be helpful for you to try if you have a telescope at home, or it's just fun to watch and you'll learn something new about sunspot, hopefully, and just solar activity. I forgot to mention, all of this equipment is part of the University of York. So yeah, I'm doing physics with astrophysics. I'm a second year, so I get to use this equipment in the university. The photo you see is taken using a calcium K filter, which has a wavelength of 393.4 nanometers. This means that this filter only lets through light of this specific wavelength, which makes the sun appear this purple magenta color. The calcium K filter is really good at capturing features on the chromosphere like sunspots and sunpores. Calcium K and calcium H filters are commonly used in imaging, but not so much while observing, as this violet wavelength is hard to see in adults. Younger observers will see the sun better in this wavelength. However, adults will have a harder time as their eyes are more deteriorated, and this is why hydrogen alpha filters are more popular for solar observing. Before understanding sunspots, we have to understand what sunpores are. They are tiny little spots of 2 or 5 minutes arc in the photospheric region. Majority of these pores don't even develop into sunspots, but if they do that very rapidly. They are of low intensity and longer lifetime than most sun granulation. Sunspots are the most common manifestation of solar activity. Both sunpores and sunspots originate from internal solar magnetic fields going through the photospheric layers. All sunspots and sunpores appear darker as they are cooler regions compared to the rest of the sun. They are still very hot though, around 4000 Kelvin. They differ from sunpores because they have an umbral region and penumbral region. They are approximately of 4,000 up to 8,000 kilometers in diameter. Although they appear small, they are actually very big in reality. You can identify the umbral region as the darker region, which is of circular shape. The penumbral region is the lighter layer around the sunspot. All sunspots appear in pairs, as this is where the plasma flows from inside to the outside of the sun. This is what causes prominences, like this one. This is a picture of the SDO captured that day, and this is the one I took. The SDO telescope one has more of a pink tinge, as it works with 170 nanometers wavelength. The SDO telescope is NASA's Solar Dynamic Observatory, launched in 2010. It goes around the Earth in a geosynchronous orbit, which is a low inclination orbit of 23 hours, 56 minutes and 4 seconds. Did you know that the sun has a cycle? We can see so much solar activity in our picture because the sun is at peak activity. It is approaching the 11th year of its cycle. As you can see from the so-called butterfly diagram, the solar activity increases and decreases every 11 years. During this cycle, the sun's magnetic field behaves very strangely. The magnetic field lines behave normally in the beginning of the cycle, but as the time increases, the magnetic field lines start bending with the direction of rotation, which causes the sunspots to move quickly at the equator and slower at the poles. This is what we call the differential rotation. At the end of the cycle, as we said, the sun's magnetic field starts acting very strange, which causes the solar activity to increase massively. As a comparison, this is the sun in 2014, and this is the sun now. If you're interested in observing the sun, this is the time to do it. Astrophysicists are now focusing their attention on studying the physical behavior of our star, as we want to be able to predict CMEs, Coronal Mass Ejections. They are very big solar flares which get ejected from the Sun, which can reach the Earth and beyond.